First plenary talk today is by Nina Zorboska from University of Manitoba. She's going to talk about localization of Toeplitz operator with BMO symbols. Nina, please.
Okay, thank you very much, Jafar. I would like to thank the organizers for inviting me to give a talk and for organizing such a great focus program. I mean, there were so many wonderful talks, and I hope my talk is not going to lower the bar too much. So this is a week on operators on function spaces. And on this page, before I give you all the definitions, I just wanted to throw in a few notions. So for example, on the operators side, I will be talking about Toeplitz and other operators in the Toeplitz algebra. The spaces that I will be mentioning will be the classical Bergman space on the unit disk and BMO spaces. And then I'll also mention the Berezin transform function. I'll define what it is, but for the moment, I find it's a very interesting idea, and I call it anti-quantization on reproducing kernel Hilbert spaces, since you go from operators to functions. Quantization, usually people refer to going from functions to operators. So here is a sample statement, again, with no definitions yet, so don't worry about it if you don't know what am I talking about. Since this sample statement gathers almost all of the notions that I've mentioned before. So there is BMO, there is the Toeplitz operator, there is the Bergman space, and there is the Berezin transform. And it's a particular problem that has generated in many different contexts an enormous amount of research. So why am I mentioning this here on the first page? Well, of course, the goal of my talk is to present some interesting results, but there is another sort of hidden agenda here, which I want to just even flag on the first page. What I really want to show is that it is one thing to know if a certain statement is true or not, but to truly understand what it is saying and how does it fit in the big picture, you really need quite a lot beside the proof itself. So just for example, for this particular statement, the statement is true, the answer is yes, and that the proof was given in 2003. But why is this true? Really took a lot, and the work which is related to the idea of localization operators from 1998 all the way up to today is really behind the scenes, which kind of put this result in context. Okay, so here is the table of contents, and almost for half of the talk, I will be really talking about the classification of compact operators on the Bergman space via the Berezin transform, and the localization ideas will be hidden in the background, while for the second half of the talk, the localization will be prominently displayed. So just to start with the notation, I will denote the Bergman space on the unit disk by LA2 of D, A for analytic or holomorphic functions, and that's the also regular L2 norm. Toeplitz operator for function in L1 of D, and P being the Bergman projection is defined as the projection of the product of two functions. F, I'll usually refer to it as the symbol, and of course G is the function in the Bergman space. It has an integral representation, which you can see here. And of course, the Toeplitz operator is just densely defined on the Bergman space in general if F is an L1 function, but if F is in L infinity, then you really have a genuine bounded operator, which by the closed graph theorem just simply means that TF maps the Bergman space into itself. So the Bergman space is also reproducing kernel Hilbert space with this particular kernel, which I'll denote by capital WZ, while with little kz of W, I'll denote the normalized point evaluation functions at Z in the disk. Now, on any reproducing kernel Hilbert space, you can define the Bayesian transform. I'll denote it by T tilde for the operator T, and it's just the inner product of TKZ with KZ. So projection of TKZ on KZ, really the coefficient in front of the projection. Now, for Toeplitz operators, their Bayesian symbol also has a very special particular representation via this integral, and I will also denote by F tilde the Bayesian transform of the symbol function of the Toeplitz operator. The Bayesian transform, or this anti-quantization, works really nice for quite a number of reproducing kernel spaces, in particular for the Bergman space, since this transform is really a continuous, infinitely smooth, real analytic function which maps operators into functions, and it is one-to-one. So the hope is that some of the properties of the operator can be described by corresponding properties of the Bayesian transform. So for example, something that's very easy to see by the definition of the Bayesian transform is that if T is bounded on the Bergman space, let's just look at our universe, which is the Bergman space, then the Bayesian transform of T is a bounded function on the open unit disk. Now, the opposite implication does not hold for every operator. So here's a very simple example of a diagonal operator. The diagonal is the sequence AN, and this is with respect to the standard basis of the Bergman space, which later on I'll actually even mention explicitly. And the diagonal has values either 0 or m, depending if the index is of the form 2 to the m or not. The Bayesian transform function can be written explicitly as this power series, and it's just calculus to estimate that the Bayesian transform is bounded, for example, by the number 6, while it's obvious that this operator is not a bounded operator because of the m here going to infinity eventually. Okay, well, another important property of operator is compactness. And on the Bergman space, it really happens that if T is a compact operator, then the Bayesian transform vanishes as you approach the boundary. The reason for that is that the normalized point evaluations go weakly to 0 as their index Z approaches the boundary. But again, the opposite implication is not true for every bounded operator on the Bergman space. And here is an example which I have given it here as a composition operator, where the symbol f of z is minus z. So this is just a rotation, which actually, if you write it out, happens to be yet another diagonal operator. Again, we can calculate the Bayesian transform specifically. Here is how it looks: 1 minus modulo z squared over 1 plus modulo z squared, the whole thing squared. And it's easy to see that the Bayesian transform vanishes as you approach the boundary. On the other hand, T is a unitary operator, so it cannot be compact. Okay, so I've started with the negative examples, even though I wanted to show you how useful the Bayesian transform is. So it is really a legitimate question to ask, okay, so then for what kind of class is theta of operators, and I'm mostly interested in bounded operators on the Bergman space, does the vanishing of the Bayesian transform as you approach the boundary imply that the operator itself is compact? So this question really generated, even in this very specific context of the Bergman space, and just even for Toeplitz operators themselves, a large amount of research. And let me just mention two with a gap of about 10 years in between. So in 1998, Axler and Zheng showed that if the operator T is a finite sum of finite products of Toeplitz operators with bounded symbols, then T is compact if and only if the Bayesian transform vanishes as you approach the boundary. So in particular, a single Toeplitz operator with a bounded symbol satisfies this property, and is in the class theta. Well, of course, finite sums of finite products of Toeplitz operators, it sort of even cries for a question, well, how about the Toeplitz algebra, which is the norm closure of the finite sums of finite products of Toeplitz operators? And jump 10 years ahead, Suarez in 2007 proved that for bounded operators on the Bergman space, T is compact if and only if T is in the Toeplitz algebra, which I'll denote by tau, and the Bayesian transform of the operator vanishes as you approach the boundary. So this is really a beautiful result. Let me just mention here that the same result, the Suarez 2007 about the Toeplitz algebra, was extended really to the standard weighted Bergman spaces on the unit ball by Mitkovsky, Suarez, and Wick in 2013. And this is the only place where I'm actually going to mention the weighted Bergman spaces and the unit ball, although most of the results that I'll mention are true in this larger context, but I just want to avoid too many parameters, so I'll really will stick to the Bergman space over the unit disk. So let me mention some of the research in between these 10 years. And since in the title I mentioned the BMO spaces, let me mention an example of a theorem which is related to the BMO spaces. So here is a standard definition of the BMO P spaces when P is greater or equal than 1 for functions f that are in the LP space of the disk. It's a standard definition of averaging things, and then there has to be some uniform boundedness. And even though I haven't defined them, this dz, comma 1/2 is really here the pseudo-hyperbolic disk, which is centered at z and with radius 1/2. 1/2 is not important. It could be any r less between 0 and 1. And f kappa is really the average of the function f over this pseudo-hyperbolic disk centered at z. Now, there is another equivalent definition by using Bayesian transforms. And since I'll mostly care about bounded operators, so for example, if it's a Toeplitz operator, then its symbol has a bounded Bayesian transform. So if f tilde is really bounded, then I can define the BMO spaces via the Bayesian transforms of the modulus of f, and you can see the definition here. It's this supremum, and I look at the difference between a positive function, which is modulus of f to the p, and its Bayesian transform with the modulus of the Bayesian transform to power p. This is usually referred to as the p mean oscillation of the function f at z. And of course, here, the way I've written, I have an extra power p here, and then these have to be uniformly bounded. Now, these spaces actually vary when you vary p, and it is true that L infinity, so the bounded functions, are included in any of the BMO P spaces, and they grow as the superscript gets smaller and smaller, and the BMO1 space is the largest of them all. And here is a result, related result to the classification of this category of operators theta. Namely, if, and this is the sample statement now written with more math symbols than words. So if f is a BMO1 function, it happens that the corresponding Toeplitz operator with the symbol f is bounded on the Bergman space if and only if the Bayesian transform of the symbol function f is bounded on the disk, and TF is compact if and only if its Bayesian transform vanishes as you approach the boundary. Well, so this is year 2003, so it's kind of in between 1998 and 2007. But now, looking from this perspective, of course, one natural question is, well, is this kind of Toeplitz operator really in the Toeplitz algebra? And I don't want to put too much mystery to this question. As you will see, the answer is yes. And that's one other explanation besides seeing the proof why this theorem holds true. Now, before I go to the actual localization properties, I also want to mention a few other results. So for that, here is a definition of what is called a radial operator. Again, I'm just interested in Bergman space. And the way to explain this is to say, well, okay, the operator is equal to its radialization, where the radialization is this average of the unitary orbit of the operator, where this UT stands for the unitary operator, which is composed by rotation. Now, it happens the radial operators are diagonal operators with respect to the standard basis. Here is the standard basis of the Bergman space. And the two examples that I gave you originally, where things went wrong with what I really wanted to work, they were really radial operators. Now, why not just call them diagonal operators? But from the prospect of Toeplitz operators, there is this interesting connection. And it just happens that if an operator is a Toeplitz operator with a symbol f, the operator is radial if and only if the symbol is a radial function. And one of the first results on this class theta was actually this result by Kornblum and Zhu in 1995, which starts with a radial and bounded function. And it says then the corresponding Toeplitz operator TF is compact on the Bergman space if and only if the Bayesian transform vanishes as you approach the boundary. Now, of course, we know from Ackler-Zeng's results in 1998 that we don't really need radial, bounded is enough. But in 1995, that was not known. So that's why this property of F being radial played a role. Well, move forward a few years. Actually, there is this more general result about general bounded radial operators on the Bergman space. And the theorem says, if I denote the diagonal of this operator by the sequence AN, I need a certain requirement on the oscillation on the sequence. So if, namely, if n times an minus 1 is bounded, then we have the result that we want. The operator T is compact if and only if its Bayesian transform vanishes as you approach the boundary. Now, of course, this is 2002. This is before the 2003 result that talks about specifically Toeplitz operators with BMO symbols, but there is a nice connection here. So first note here is, of course, to compare to the previous theorem of Kornblum and Zhu from 1995. If F is radial and bounded, and we look at the Toeplitz operator TF, which is a diagonal operator, then the oscillation criteria on the diagonal sequence is automatically satisfied. So the 2002 theorem is really a generalization, even from the perspective of just Toeplitz operators. And it also happens that if F is radial and F is in BMO1, with the corresponding bounded diagonal radial operator, then again, the oscillation on the diagonal sequence is true. So a nice circle of ideas that connect very nicely. And here is Suarez again with the result, in 2008, which really sheds some extra light on this kind of results about radial operators. So he proved that if T is a bounded radial operator on the Bergman space and the corresponding diagonal sequence satisfies this same oscillation criteria, then the operator is actually in the Toeplitz algebra tau. So from the perspective of his 2007 theorem, you see now really the whole picture and what's really happening here. Let me just mention here, it's a very nice paper, and he actually classifies all of the radial operators which are in the Toeplitz algebra. It is almost the oscillation, but there is a slightly more, since actually there exists a radial operator T in the Toeplitz algebra such that this oscillation criteria is not satisfied. Let me now jump way ahead a number of years and finally start using the word localization or localized operator. So in 2015, Izraelowicz, Mitkovsky, and Wick had the following theorem. So I'll define localized operators in the next page, but here let me just say that T belongs to the C-star algebra generated by the weakly localized operators, which I'll define in a moment, on the Bergman space. Then T is compact if and only if its Bayesian transform vanishes as you approach the boundary. And the same year, just a little bit later, Shia proved the following result, namely the C-star algebra generated by the weakly localized operators on the Bergman space is nothing else but the Toeplitz algebra. So a really very nice full picture now. And this, as you will see, property of weak localization then, what it does is just also gives us a tool to check if a certain operator might be in the Toeplitz algebra or not by checking is it weakly localized or not. Because actually, given a general operator, it's very hard to check if it's not just the standard Toeplitz operators with a Toeplitz operator with a bounded symbol or compact operator, is it in the Toeplitz algebra or not? So just to relate to a few of the things that I've mentioned previously. So for example, if F is in BMO1 and TF is bounded on the Bergman space, is the Toeplitz operator TF weakly localized, which will then furthermore say that it is in the Toeplitz algebra. So before I continue with the follow-up results, let me just define what is weak localization and what is a weakly localized operator. So here is disk automorphism, size Z of W for Z in W in D, Z minus W over 1 minus Z conjugated W. And here is the definition of pseudo-hyperbolic distance on the disk. I'll denote it by rho of ZW, which is just the modulus of this disk automorphism. And here is a definition of the pseudo-hyperbolic disk that I already mentioned before, where R was 1/2, but for any R in 0, 1, we can denote the pseudo-hyperbolic basic disk centered at Z with radius R. These disks are actually Euclidean disks, and the Euclidean radius is different than R, and actually if Z approaches the boundary, this Euclidean disks become smaller and smaller and smaller. So a linear operator will be called weakly localized, or sometimes I'll write T belongs to AWL for weakly localized, if there is this constant A between 0 and 1, such that for the pseudo-hyperbolic invariant measure d lambda, which is just the usual normalized Lebesgue area measure of the disk dA with this extra weight there, and not to have to write two separate lines for both T and T star, let me just say R is either T or T star. So both for T and for T star, there are these two conditions that have to be satisfied. So what are these conditions? something has to be uniformly bounded for every point in the disk. And what is that? Well, it's an integral in which you see the norms of the point evaluations, and you see this inner product of the operator and then the normalized point evaluations. So definitely this is something that you can define in a much more general context for reproducing kernel Hilbert spaces, which have behind the scenes some measure and some distance over the domain of the functions. So the first condition basically guarantees that the operators T and T star are bounded. And the second condition, you see this limit as the radius goes to 1. And again, something has to be uniform, behaving uniformly. And then the integral is actually over the complement of the pseudo-hyperbolic disk at a point Z. And this limit has to be 0. Then we say that the operator T is weakly localized. Well, it's a very nice condition because I've already revealed what that provides. So let me just maybe say a little bit, because it might be really a mystery. Where does the name localization and why weakly localized operators? Well, in the paper, well, where this notion was defined and introduced, that's the 2015 paper by Izrailovich, Mitkovsky, and Wick. Let me just mention a few of the important ingredients of the paper, and you will see where the word localization comes from. So they've proved that each weakly localized operator can be approximated in the operator norm by infinite sums of well-localized pieces, which are operators of the following type. So now this is actually an operator from the Bergman space into the L2 of D space. And these are multiplication operators on L2, really, with characteristic functions over some sets. And what are the sets? Where, well, these sets Fj and Gj form a covering of the unit disk. So you can imagine that there are even some pseudo-hyperbolic disks where Fj's, the family of Fj's is disjoint. Gj's are slightly larger, but each point in the disk can be in a fixed finite natural number times of Gj sets. Okay, so that's where the localization word comes from. It happens that each Toeplitz operator Tf, when F is bounded, is weakly localized. And the set of weakly localized operators has a nice structure. It is actually a star algebra, and its norm closure contains the Toeplitz algebra. That's what was proven in this 2015 paper. Well, as we know from the later Shia result, it just really happens that the norm closure is exactly equal to the Toeplitz algebra. Okay, and then since the motivation for all of this was the compactness of operators and Bayesian transfer vanishing at the boundary, well, I'm not going to show you why for weakly localized operators that's true, but let me just mention, here's what's behind the scenes. What is special about weakly localized operators is that you can estimate the essential norm by this lim sup as modulus of z goes to 1 of the supremum over the points in the pseudo-hyperbolic disk centered at z of the modulus of the inner product of tkz with kw, kz and kw being the normalized point evaluations. So there, it's one step ahead to really have the full characterization of compactness of weakly localized operators via their Bayesian simple vanishing at the boundary. Okay, so great results. But if one deals with specific operators or specific class of operators, one can ask the following questions. Are there actually any other stronger but possibly easier to check localization conditions that will determine when an operator is in the Toeplitz algebra. And actually the answer is yes, and those are the notions of sufficient and strong localization. So what are they? How I'm going to define them? Well, in order for them to be defined, we need these unitary operators that are related to the disk automorphisms. So for a point in the disk and a function, a holomorphic function in the L2 space, we define the unitary operator uz. You compose with the disk automorphism psi z first, and then you multiply with the normalized point evaluation. These are unitary operators, and they're very special. It's not that only uz equals to uz star. On top of that, uz equals to uz inverse. And they really shift around the normalized point evaluation kernels in a very nice way. uz or kw is just norm 1 constant times the normalized point evaluation at the point psi z of w. So here are the definitions of strongly and sufficiently localized. For an operator in the Bergman space, we say that it's going to be a strongly localized or sufficiently localized. If, well, for the strong localization, we require that for every p greater or equal than 1 less than infinity, these two supremums are finite, while for the sufficiently localized property, we only require an existence of p strictly greater than 3, such that these two supremums are finite. And what are these supremums? Well, in some way, these are orbits of the operator with respect to these unitaries at the constant function 1, and then you take the p norm, and you want the p norm to be uniformly bounded in z, both for the operator t and for the operator t star. Now, of course, every strongly localized operator is sufficiently localized, and a little bit about the mystery about why this p is strictly greater than 3. Well, the answer is it will work for what we want to get out of them, but maybe just to mention, it's very clear that p equal to 2 will not do if we want a single p, simply because if you look at the 2 norm of the Mobius or disk automorphism orbit of t at the constant function 1, that's just the norm of t at the normalized kernel kz, and they're of norm not 1, so the 2 norm is definitely bounded uniformly for any z just by the norm of the operator t. Well, you'll see a little bit further on why this p is strictly greater than 3. It really has to do with the use of Schur test and some Forelli routine estimates that you needed. So just a little bit on the history of these notions. Well, sufficient and strong localization criteria were actually behind the scenes of the proofs of, so the sufficient localization worked in the Exler-Zeng paper and results from 1998, and the strong localization showed up in the proofs in 2003 of the Toeplitz operators with BMO1 symbols, characterization of compactness. So again, these were results which were showing that certain operators, the vanishing of the Berezin transform implies compactness. So the term sufficiently localized operator actually showed up for the first time in 2013, and it was used by Xia and Zeng in their paper, which deals with the Fock space. I'm not saying anything about the Fock space, so it's basically similar kind of characterization of compactness via Berezin transform for sufficiently localized operators, and they define sufficiently localized operators to be the operators for which there is an upper bound on the inner product of TKZ with KW. This F stands for the normalized point evaluations for the Fock space. Let me just give a remark that actually there is a certain definition that resembles their condition, and if I call this inequality star inequality. So again, we're looking at the inner product of TKZ with KW. And if I can find an upper bound, and you see the disk automorphisms show up here in the Fock space, it's the translations that play the role of disk automorphisms. And that showed in the specific function, which was the upper bound for the inner product. And if you require that this capital F of, which is a radial function of modulus of U, is an LP function for some P greater than 3, then it's not too hard to see that if T satisfies condition star, then T will be sufficiently localized on the Bergman space, since this Mobius orbit, it's in its P norm will be less or equal than the constant times the P norm of the function capital F. I'm not going to go into any more details, but I just want to mention there is some geometry behind the scenes. Okay, so if we jump to more recent days, here is a theorem which is a joint result with my former PhD student Mohamed Sadeghi from 2020, which says that if T is sufficiently localized, then T is weakly localized, which really says that also every strongly localized operator is weakly localized. And just for the flavor of things and to see why sufficiently localized is P greater than 3 works, just to mention the main parts of the proof. So remember, for sufficient localization, the definition was that this supremum, both for T and T star, of the P norms of the orbits of T is uniformly bounded. It just happens that if we choose, so here is, I know you have not memorized the definition of weakly localized, but this supremum here that you see of this integral was property 1, and it had to be true for both T and T star. So if you look at this expression, any A between 0 and 1 would do. And here, the one that works perfectly is if I choose A to be equal to 1/3. And that has to do with P being greater than 3, because really that's 1/A. And in order for Rayleigh-Rudin estimates to work and for some Holder inequalities to work, we really need P to be greater than 3. And that's the smallest possible one. You can manipulate A and wiggle it around, but any other A will give you a larger P. So really, the nicest one is when A is 1/3, because then P is smallest in some sense because it's greater than 3. So in the second part of the definition of weak localization, this integral over the complement of the pseudo-hyperbolic disk, first of all, for any z, if you take the supremum over z, and then if you take the limit as r goes to 1, had to be equal to 0. So all that I'm going to say is that if you use Rayleigh-Rudin estimates and then Holders, you can estimate this integral with an upper bound, which looks like this. It's the P norm of the Mobius orbit of T at the point 1, which, if T is sufficiently localized, its supremum will be bounded. And then the rest is really 1 minus r squared to this exponent, which if you choose Q to be a number between 3 and P, so that P minus Q is positive, this is positive. So when r goes to 1, this goes to 0. Okay, so it's just a technical kind of tweaking of things that will do the job. Okay, so we can use this to really, and here is a reminder of how I view the space BMO1, the second definition that I gave you via Bayesian transforms. So if I want to talk about localization of specific Toeplitz operators with BMO symbols, here is another result from the same paper, which really says that if f is a BMO1 function and its Bayesian transform is bounded, which is really saying that the operator itself is bounded, then TF is really strongly localized, which means it's sufficiently localized, which means it's weakly localized. Now, it's interesting maybe to just see the ideas of the proof, and here are the main ingredients. So if I compose F by a disk automorphism, I will still be in the BMO1 space. That's true in general. And then that means that if I look at the orbit of TF at the constant function 1, this is nothing else but actually yet another Toeplitz operator with the BMO1 symbol at the point 1. And then we use that the Bergman projection P maps BMO1 boundedly onto the block space. And the fact that the block space is continuously embedded in any of the LP spaces over the disk when P is greater or equal than 1 gives you what you want to have. Okay, so now you can see that as a corollary, we really get that if F is a BMO1 function with a Berezin, bounded Berezin transform, then the Toeplitz operator TF is really weakly localized, which furthermore, by Shia's result, says that this is an operator in the Toeplitz algebra. So here is now a backward view of the 2003 result. If we kind of start backwards first with Shia's characterization of the Toeplitz algebra as norm closure of weakly localized operators on the Bergman space, and Suarez characterization of compactness via vanishing of the Berezin transform for operators in the Toeplitz algebra, you see why the 2003 theorem is true. It is true since TF is really in the Toeplitz algebra. So I find this kind of nice and neat that you need a number of years to really understand sometimes what's really going on. Okay, so for the last part of my talk, I want to mention localization of Toeplitz operators with measure symbols. And even though originally it might look like a separate kind of idea, to show you that this is very much connected to what I was talking about just right now, and that 2003 result pop-ups once again. So just to remind you, for a complex Borel measure, so complex Borel measures I'll denote by nu, the Toeplitz, corresponding Toeplitz operator is defined similarly as when the measure is induced by a function. So it's an integral formula. Here is the Bergman projection part, and then we integrate with respect to the measure. Of course, positive measures are particularly nice. So if mu is a finite positive measure, so to distinguish between complex and positive, I'll use mu for finite positive Borel measures on the unit disk. This has been mentioned many, many times, but let me just mention it in this particular format. Mu is a Carlson measure for the Bergman space if you can find a constant such that this inequality holds, and we really have this embedding of the L2 Bergman space into L2 the nu space. Now, for positive Toeplitz operators, both induced by functions and by measures, the results, which I didn't state, really are very nice and are sort of a similar kind. I just want to mention this combination of results of Hastings from 1975 and Lueking 1987, who really introduced Toeplitz, started doing results on Toeplitz operators induced by measures. That for a finite positive Borel measure, mu, the corresponding Toeplitz operators T mu is bounded on the Bergman space if and only if mu is a Carlson measure for the Bergman space, which is also equivalent to the Berezin transform of mu being bounded. And of course, this is what I'll need, but there is, if you're wondering, there is a corresponding vanishing Carlson measure and Berezin transform of mu vanishing at the boundary compactness characterization. But the positivity here is very important. So here is a theorem from the same 2020 paper, where we proved that for some special complex Borel measures, nu, for which their total variation is a Carlson measure, we have the sort of weak localization behind the scenes. Namely, the Toeplitz operator T nu is weakly localized on the Bergman space, which means that these are operators in the Toeplitz algebra. Well, more recently, it turned out that actually more happens to be true. These kinds of operators would not be just weakly localized, they're actually going to be strongly localized for new complex Borel measure with total variation being Carlson measure. The corresponding Toeplitz operator is actually strongly localized on the Bergman space. And I'm saying this because there is this further connection to the strong localization of Toeplitz operators with BMO symbols. One more time, yet another perspective and another view of that reoccurring result. So here is a following proposition, which in some way connects the measure theoretic aspect with this space of BMO1 functions. So if nu is a complex Borel measure on the disk, which is absolutely continuous with respect to the normalized Lebesgue area measure, here is what's true. Its total variation is a Carlson measure for the Bergman space, if and only if the corresponding Radon-Nikodym derivative f is actually a BMO1 function for which the Berezin transform is bounded on the unit disk. So now, here is one more time stated as a corollary with sort of all of the bits and pieces that are kind of connected for this particular case, namely Toeplitz operators with symbols that are in the space BMO1. So one more time, if f is in BMO1 and the Berezin transform of f is bounded, which implies that the operator Tf is bounded on the Bergman space, here is the three ingredients that kind of come nicely together. Tf is strongly localized, which was really actually, if you look into the proof of the 2003 result, almost already there, which means that it is weakly localized. And so by Shia's result, it is in the Toeplitz algebra tau. And then by Suarez's result from 2007, the compactness of Tf is completely characterized by its Berezin transform vanishing as you approach the boundary. So that's it for my talk. And here are some of the references, as many as I could fit on one page. And thank you very much.
Thank you indeed, Nina. Let's thank the speaker. Is there any question or comments for Nina?
This is Sheldon Axler. I have a brief comment. Thank you for the terrific talk. It helps me understand something, actually. In our 1998 paper, Zheng and I had to use an L6 norm, where an L2 norm may have been more natural. And I was just looking at the paper, and we wrote a comment there saying this is a little strange, but it doesn't work with the L2 norm. Yeah. And I think going to this sufficiently localized criteria helps explain why. My memory is that we used 6. We could have gone lower, although not all the way to 2. 6 just made the arithmetic easier.
Yeah. Yeah. Well, it's interesting. And actually, p greater than 3 really stems from the methods that are used. So it's still a question. Well, okay, p equal to 2 is not going to do, but will some 2 plus epsilon do? And as far as I know, that's still an open question. Of course, you have to use completely different methods in the compactness characterization via Berezin transform if there is any hope for 2 plus epsilon to work.
Any further questions or comments? If not, let's thank Nina again.